Yes, we are live, and maybe Eric can introduce the
Hmm?
guest today we have.
Yes, today we are joined. We are happy to be joined by two engineers from the MoonBot project, which is a project in Japan led by the University of Tohoku. So it's a university in the north part of Japan, pretty big in space in such kind of topic. Wow, and it's sponsored mainly or maybe essentially by the government. Okay, there is a program in the Japanese government. So sorry, the keyboard. I can
Oh,
only hear the keyboard.
that's me.
um,
My bad.
no problem. Sorry. Um, so in the US we have DARPA and such kind of, and maybe NSA. I don't remember the names. Okay. So in Japan there is something called the NEDO, and the NEDO has a series of a pretty big 5 year or more funding systems. Okay, and one of them is called a series is called the Moonshots. Okay, and one of them is literally to go to the moon. Okay, it's called MoonBot. Okay, which is about robotics. Okay, that have a very specific features. Okay, and Eliane and Shami are two engineers. Okay, I think Eliane is doing his PhD thesis during this project, and Shami, perhaps your master, perhaps
Yes,
master
that's
thesis.
right.
Yeah,
Yeah.
and so they are active core engineers on the project, and very happy to have them today to talk about it, to present what they're working on, and after to have an exciting Q&A.
Uh, Maybe we can have a short round of introductions. I can start. So I'm Anuraj, and I'm currently based in Finland. So I'm a roboticist, a space roboticist by education. And like I've been working with these guys for now around 5 years. And yeah, so by profession, I'm mostly a consultant for robotics and embedded systems. Yeah, that's it from me. Eric?
So actually, I think everyone knows me here in the group here. Okay, so I'm an engineer and scientist. Okay, working mainly on software. Okay, so applicable mainly to AI and to implemented robotics. Okay, working from Japan, and currently working with Liam, who is here. Okay, and Eliane and Shami, who help us see how what we develop at the company with Liam can be useful to help in developing actual robots. And so it's super exciting because our tools, we have a couple applications to the space industry, and one of the main ones is the MoonBot project they are working on. Next is perhaps.
Yeah, I can go next. Hey guys, I think Liam joined us once before, maybe. Yeah, I remember meeting you. I am Venkat and I live in Seattle. Long ago, my background was in aerospace control theory, but I haven't done technical work for more than 15, 20, yeah, 15 years or so since I left Xerox. These days, I'm mostly a blogger and management consultant. But this Yak Rover hobby project is the only chance I get to do at least a little bit technical work, so it's fun.
I'm Ellen. I've been interested in robotics for many years. I was in a high school robotics competition. I'm in Waterloo, Ontario, Canada. I have some training as an engineer, system design engineering, and I'm just kind of interested in all this stuff.
I guess I'll go next. So yeah, it's my first time here, and I'm Eliane Nepel. I'm French and now studying in Tokyo Daigaku in Japan, and I'm working on space robotics, and I'm doing a PhD. And yeah, my background has been more in mechanical engineering, but once I arrived in Japan, I transitioned into learning software, and now I'm mainly doing software.
And I'll go next, I guess. Thanks for inviting. Thanks to Eric. We have this opportunity to present our project. My name is Shamistan. I'm from Azerbaijan, and as alien, I came to Japan to study in Tohoku University. We are in the same lab, Space Robotics Laboratory, and we mainly work on this project called Moonshot project that we develop MoonBots. Yeah, and right now I'm doing my master's, currently in my last semester, and busy with my thesis and stuff like that. It's nice to meet you all, and hopefully we'll have a great meeting today.
I guess I can say hi. Hi, I'm Liam, and I work with Eric as a DevOps engineer for Artifacts, and I'm very interested to see what the MoonBot project is all about.
Thank you. And should we get started? Perhaps, Eliane, perhaps you will have some introduction.
Yes, exactly.
Just
For how long should we take for the slides and introduction? Just so I know I don't want to take too long.
So generally we meet for 1 hour. The meeting,
Okay.
like, yeah. So like, we can go a little bit over time. Like those who want to leave
Okay,
can
okay,
leave.
okay.
Yeah. So if you want to share something, there should be a button at the bottom of the screen, like a plus screen, and then you can share your
Yes,
screen
I
with
do
that.
that. Share screen. Okay. This one, no, wrong screen. This one. Okay, let's go. Screen is here. Okay, you should be able to see it.
Yep.
So for today, in the introduction to the MoonBot and Moonshot project, first I don't want to introduce the deep goals of the Moonshot project. I think everyone here is more interested in making cool robots. So I mainly want to showcase the robots, what we are doing with them, instead of saying, okay, why do we do that to go on the moon, and why did we decide this? Also, we are a research laboratory made of students, so not professionals. So there are also some things to consider about that. So I mainly want to only show the robots, the tools we develop for them, and what we are doing with those robots that are pretty cool. And because I work in software, we'll first start talking about the robots, and then continue on to the software side, which is my job. And Shami will, I think, talk a little bit also for his slides. So, what's the MoonBot? The MoonBot is this set of robots right here. And the MoonBot is part of the Moonshot project. So the MoonBot is a modular robot. So this way we can have several parts of the robot, send all of those parts on the moon, and on the moon we can assemble the robot in the shape we need for the mission. And as the mission progresses, we can then change the shape of this robot to do a new mission. And here we have those basic building blocks of the MoonBot. We have the limb, the wheel, and the body. And with those, we can make already different shapes. For example, the minimal, you can see at the bottom left of the screen, that's just a wheel with a limb. And this minimal can actually move a little bit on the sand. It's not very effective, but it's already something. Then there is the vehicle, the second on the left, that very looks like a small car. It's simply two wheels connected to a limb. And with this, we can drive around very easily. Then we have what we call the dragon, which is basically the vehicle where we add a limb on the front. So this is better than only the vehicle because we can do manipulation tasks at the same time. The vehicle is actually pretty useless because it can only move, but it cannot do anything else. And then we have the tricycle, the bottom at the bottom right. This one is quite massive, with 3 wheels, 3 limbs, all connected to one central body. And this would be used, for example, to carry heavier loads in the central body. We'll see more video of those later. So first video to introduce the modularity aspect of everything. So this is my upcoming paper is the video for my upcoming paper at iSparrow. So you can see we can assemble those robots together. Here is a 3 degree of freedom limb that we connect to 2 other wheels. And you can also notice that the robot is actually quite big. So it's quite dangerous to work with also. And then this, we can simply drive it around on this simulation test field that was at DLR, Germany. We went there. And just drive and explore just with this vehicle configuration. And for assembling, this is actually the job that Shami, that is here today, of automating the assembly. Here, his algorithm will go towards the wheel with one of the limb, and then it will grasp automatically the grasping point on the wheel. And then the wheel can roll away. From those, oops, can I go back, please, for Google Sheets? Thank you. Yeah, and don't on my first. Okay. From this minimal configuration with only one limb and one wheel, we can then connect them together to create a dragon. And here we can close the gripper and it can roll again. And from 2 dragon now, we can once again connect both of them to create something that we don't have a precise name for it. But sometimes we call it the Shinkansen MoonBot, because there are many, many different parts and it looks like a train. And we can steer that, go somewhere, detach, and once again, continue onto a mission. So that's the introduction of the modularity side of the robot, that for us is the main goal of this robot. Of course, the main goal is also going on the moon, etc. But as the developer of this robot, that's what we are currently focusing on. And for assembly, we have, this is a much older video. As you've seen before, we have, Shami has improved this a lot, but here we can again connect to the wheel. Oops. Okay. We can connect to the wheel. This is an older version of the robot. Connect to the wheel and then drive away. This is very old video, so it doesn't look that smooth. It has been improved a lot through time. Here for transportation, we actually can drag stuff on the ground using the minimal configuration. And here, for example, we bring a solar panel inside of a sledge, and then the dragon that is able to locomote and also manipulate will place the solar panel upright. And once we do that, we can kind of build a moon base. That's also a goal, is to build a moon base, even though right now I'm more focused on modularity and the robots.
So, sorry, is this automated or is it a remote control on this video?
Yeah, in this video it is teleoperated.
Okay.
So no remote control yet.
Thank you.
Sorry, I'm keep switching slide because the playing videos in Google is not okay. But yeah, it's teleoperated for now. And even teleoperations of those robots is actually very difficult, as we'll explain on the network side, the software side later, especially for us that we are just students. And there are many, many motors to control using inverse kinematics, synchronizing the wheels, etc. That's already very hard. We have some more manipulation video. This is just to show off maybe the inverse kinematics that are working. So here we have actually some kind of it looks like it's an inflatable module, and we want to place something and interact with the inflatable module to maybe do some repair or do some inspection. Or here we place a block to stop it and maintain it so it doesn't roll away. Yes, and this was the very first version. So again, we've done lots of improvement since then. We'll see later. And locomotion, this is the tricycle that we can see move with those 3 wheels and navigate. We are not focusing that much on the tricycle right now because it's not very, we found it not very useful in the end. Yes, so those are the cool looking robots we have. And now for the new version, first we did a quite big demo in this sand field. This sand field is in JAXA, by the way. So in there, now it's automated. So you can see one of the, wait, if I can take laser pointer. Okay, it doesn't mark over the video, but basically one of you have the vehicle that is here under my cursor on the top left. This vehicle will start moving automatically towards one of the limb that is around here. And you can see actually the limb on the right top camera there. So it starts automatically going towards the limb. Then Shami's algorithm will start automatically connect to the vehicle. And once it's connected, it forms a dragon. And then this dragon has a manipulator and can continue to locomote somewhere else. And here you can see that compared to the videos before, it goes much faster and much more smoothly. Then we had the second dragon in the back that were running on the same network. Networking is a huge issue we face. And this one will actually go towards the inflatable module, which is this white thing on the back there, this white cylinder. And actually it is also automatically guided towards it, this time using a camera system to find where is the inflatable module and automatically steer towards the inflatable module. And it will slowly go towards it. It went towards it quite a bit too well and went to collide with the other robots that were on the field. So there was this, but it actually went there. Again, the assembly by Shami, I think he will show better videos than this just a little bit later. And we've also already seen many of them. This is actually the 4DOF limb module that's not made by neither me or Shami, someone else in our lab. And it's also very cool because they can assemble themselves to go from 4DOF, then they connect, and now it becomes actually 7 degrees of freedom. And it forms a bigger limb. And okay, there is no. Okay, and those can also be used for this kind of cargo transportation. If you remember before, we had the tricycle with 3 wheels. This one is actually a bit more lightweight because there are less motors, and we can once again steer around, etc., etc. On the that's Shami's slide. So if you want to take on from there.
Thank you, Elian. Could you please start the video? We can just continue sharing this one. So right here is one of the configuration that Elian was explaining. For example, the tricycle. But this time it also has a manipulator on the top of the body. This experiment has been conducted in the lab. And as you can see, the legs that are basically the same manipulators as the arm on the top, they are acting in this experiment as a height extension and going down closer to the ground. And thus it allows the manipulator on the top of the body grasp the solar panel and transport it. And then, of course, they can raise up, and everything is being synchronized by the software that Elian has developed. And I believe he will talk about this a bit later as well, in more details. But utilizing this software, as for example, Liam asked about the shared data bus. There is nothing like that. So basically, the software is the master in this case. It is conducting everything, so nothing gets stalled or left behind and stuff like that. Yeah. Can go to the next slide. This right here is autonomous assembly of one of the configurations. So from the pallet, arm attaches to the vehicle, building a dragon. And after this has been done, the same dragon that was configured gets reused on field by utilizing the manipulator to transport another module. As you can see right now, the manipulator has attached to the wheel module, and the dragon configuration has been successfully assembled. And of course here, the same dragon is reused to, again, autonomously grasp the sled and transport it. The idea is also, in this case, software-wise, to reuse the same controller for different configurations, for different manipulator configurations. So that's my work, basically what I've been doing here, developing a controller that can be reused across different platforms without any big tunings or changes. Actually, Elian, can you exit the slideshow and start again? I think I added one more. Yeah, after this one. The one before. Yeah, the one before. The one after 16, slide 16. Yeah. Yep. So this is the video that I have submitted for the conference. It's gonna be in December, actually in our city. And this is about the controller I've been talking about. You can skip this part. We already showed the dragon part. Yeah, but the idea is, as you can see, the controller is reusable over different configuration and even different manipulators. For example, right here we have the V1 configurator, the old version of the arm, doing the assembly or grasping on a manipulation task. And after that, we have the same controller running on a different kinematic chain of a manipulator and performing the same way, and doing a self-assembly, for example, in this case. So tasks are different, and robots are also different. The configurations are different, but the controller is being able to adapt and also assemble robustly and stably. I think I can go next.
Yeah.
Okay.
That's it for you?
I think for now, yes. Maybe later as well.
Okay.
Yeah.
Interrupt me later if
Yeah.
if I miss something.
There's also a lot of questions that people are asking, so I could go over that later as well.
Yeah, okay, but let's go over that right now. Before talking software, let's have a small break and talk about just the robot itself before everyone forgets about the robot itself.
About the controller, so where is the software running that controls the...
That's actually the software side, which
okay,
is
it's
coming
using
up.
MoonBot. Yeah. Okay.
No, it's not using MoonBot. It doesn't work with MoonBot. We develop something else.
Okay.
But if I can click on this.
Hardware.
It's actually a very distributed network where,
Okay.
if we focus
Maybe
just on
we can go the
Yeah.
other questions and then software.
Yeah, we switch to software later on networking.
Yeah.
Yeah. Regarding some questions that I saw in the chat about the hardware, yeah, as I said, it is custom-made hardware, and right now, actually, in this presentation, we have presented only the version 1, which is this one, and version 2 slightly, but there's also another version, a newer version, that we have presented at Expo, Osaka Expo, World Expo. And actually, that one you can see on the tricycle manipulation that I have added. Yeah, so that one is the newest version, and every time it has been like newer version. It's of course improving, a different power source as well. It's of course under the hood. It's using a battery. Like for the arm or for the wheel, but overall the power structure has been improved. It is using a thing called a battery management system to basically manage the flow of the of the power and stuff like that. And newer versions of the hardware also have a chain charging, let's say. So for example, as we mentioned, this arms connect the wheels a lot, and they also connect in, for example, series or parallel, and etc. And every gripper um, has a connector that attaches basically to the grasping point of the wheel, also basically transmitting the power. So if we have external power, for example, connected to the end of dragon, which is one of the wheels in the back, the power will get transmitted up to the manipulator. So this way we can easily charge the robots as well, much faster, using less power supplies and less cables and stuff like that. But also they can transmit power in between, even if there's no power supply. So they basically kind of use a unified and centralized power supply when they are attached to each other. Then also,
How is
When
the
you read, I can.
recharging of the power source?
just using basically normal power supplies. We attach,
Yeah, the BMS inside handles the balancing of the batteries and charging of the batteries, and so we just have to plug a 24-volt power supply, and then all of the modules that are connected together, if they are the latest version, they will then share this 24 volts between all of the BMS.
Yeah.
So on the moon, it will be solar panels, right? To charge the robots?
That's the idea.
Yep. Actually, one of our students also has been researching different ways of charging. For example, it's really not my field, but it's microwave power transmission. So using microwaves to charge the robots, which is also another interesting way. But still, of course, research progress, and hopefully we can find some feasible ways to implement those as well.
Yeah.
Is there any other question?
There was a question about how the arms communicate.
think that's
Usually now
also
we are only
software,
using
right?
Wi-Fi. Yeah, we will see that later. It's only Wi-Fi, and right now they are on those videos. They do not communicate between each other.
Oh, there's a
but we are
question.
currently working on a mesh network to do that.
Yeah, there's a question about materials from Ellen. So materials are mostly that are used are kind of like mix of PLA and carbon fiber. So it is not. That's the outer casing, of course. The actuators are mainly aluminum alloys and stuff like that. The gripper as well. Gripper is not. I would say also not fully aluminum. Some of them is just plastic PLA. So it's not really heavy, but because it's like really big, the overall just one arm, for example, is around 20 kilos, and the wheel is around 25 kilos. And of course, it also depends on the versions of the hardware, but it's around like something like that. So you can imagine when it's like a Dragon, for example, it becomes around like 90 kilos. Tricycle is like more than 130, I think. So it becomes really, really heavy.
Is the hardware ready for space?
No, it's not
No, right
space
now,
ready
no.
yet.
No.
Is there
As I
any
said
plan
at the beginning, we are more students right now, just
Mhm.
doing research and learning on this MoonBot platform than getting ready for launch.
is
Do
the
you
arm
think?
hard? No, go on, Eric.
Oh, I was just wondering whether the space version would be heavier or lighter.
I actually don't know. For the space version, of course, we want to be lighter to reduce the cost. But maybe lighter will not be possible with space-ready hardware.
Hmm.
Is
Thank you.
the
Sorry.
arm also completely like custom built, or are there like parts you can buy from some vendors?
Um, I mean,
The
mainly,
arm.
the arm. Yeah, the arm is. I mean, it's mainly custom made. The actuators are custom made as well. It's just the motors and drivers we use, of course, like commercially available motors, Maxon motors, actually. Um, yeah, but everything else is pretty much custom made.
How much of the hardware is like open source or planning to be open sourced? Is
We
there
have
any?
we have published a paper recently, and we go in details there about the hardware. I can send the paper in the chat, I guess.
Yeah.
Venkat is asking what's making the hardware heavy.
What maybe the mainly. Sorry, I'm just looking for the papers on the software at least. Yes, on the software, there is my paper that's called Robust and Modular Multi-Limb Synchronization in Motion Stack for Space Robots with trajectory clamping via hypersphere. Okay, it's a long title, and I also have a website and everything open source to do all of this. But I research the software later. And yes, for the hardware, we have an upcoming paper.
Yeah, the thing is about why it's so heavy. I think mainly it's about the actuators, because every arm, for example, have every arm has like 9 actuators, and of course all together, and also the battery. Yeah, I think that's
Battery.
most of the payload. In the wheels, that batteries are much bigger. Also, there's different sensors, more type of sensors. Like a wheel has a lidar as well, and yeah, even though it has less actuators, it's just heavier because of the battery size, more sensors. It has grasping points that are also a bit heavy.
Yeah. Actually, if you compare to other robotic arms, yes, it's very heavy, but usually standard robotic arms, they put most of the weight at the base of the robot. And we don't have a base. So the weight on one side has to be the same weight as the other side. And so that's why end effector, there is no end effector side. So everything, we cannot have a base that's on the ground and where all the weight will always be on the ground. There is always half of the weight on the ground, half of the weight on the end effector on the other side. And so that's why we need strong motors with high reduction ratios, because we cannot rely on a fixed base to take the weight. and all of the motors must be able to take the full weight of the limb, and especially the grippers and fixture point or grasping points are also very heavy because they need to be strong again to take all of this load. Because imagine this arm that's around between 10 and 20 kilos depending on the version, suspended like that on just this small gripper down here. It's actually quite a lot of torque to bear.
I think we can move on to the software now, right?
Yeah,
Okay.
I think
we talked about everything on this side. If there are more questions in the chat, we can answer later, of course. So let's continue on the software, which is more of my job. So I can answer the questions much better and much more in depth about this. So first, we want to work with modular hardware. When I started working on the software, I noticed that if I want modular hardware, I also need modular software because I cannot reuse the same software everywhere. It has to be modular also. Modular software and hardware means that the software then has to be module or robot agnostic. So it should be able to, it should be usable on any robot. So when you think of robot agnostic software and ROS2, that's very popular right now, you of course think of MoveIt2, where you can just give it a URDF and it will compute the inverse kinematics or the trajectories you want. But there is a quite big problem with MoveIt2 that makes it not usable for us, is that it's only usable for one limb at a time. And we do not have that. And it's also only for manipulation tasks. As you've seen, we have those rotating the wheels, steering the wheels left and right, all of this. And also we have to change the configuration and change the URDF quite a lot. And MoveIt, when you change the robot, you have to reconfigure everything in the settings. You have to say, okay, there is this joint here with this torque, this joint here is this torque. Every time we change the robot, that takes way too much time to do. So we had to develop on our own custom software, which is the motion stack I quickly showed before. That's open source. It works on ROS2. I'm currently switching to Zeno also to be pure Python and Zeno. And it's robot agnostic. It has distributed operations. So that means you can have several robots in series parallel as we've seen before, but also distributed controllers. So that's very nice when we do the experiments you've seen before. Actually, there is not only one student controlling the robot on the network. We are actually 3 or 4 students all controlling the robots at the same time on different PCs, and we just choose which robots we want to connect to. And that's also extremely useful to collaborate between controllers. When I say controllers, it can be operators, AI or algorithmic controllers. And the motion stack also provides an API. So there is the low-level API that is used to interface with the robot and that the robot developer should make. There is the launch API that basically launches the right things at the right place. So when we change the shape of the robot, it's the launch API that will then choose what to launch where. And the high-level API, this one is for the students or users, so they can quickly connect to the robot and send commands to the robot. And the network, so it's quite small, so let's zoom in. Network is a huge problem for us because we have so many robots that are communicating over Wi-Fi, so many students at the same time on the network. Those robots are not connected together. We easily have 10 different robotic modules on the same Wi-Fi at the same time, plus, I don't know, 10 students doing different things at the same time on the network. And we cannot, we must have high reliability to not break the robot when everyone is doing this or slow down the work of anyone. So for the network, what my goal is to have this kind of, this is more theoretical, but it has some links with what we are doing right now. We would have this Moonbase with some databases, computations, and sensor also inside the Moonbase. And all communication on the Moonbase is just peer-to-peer. If we talk about, and that's why I want to switch to Zeno also, is because with Zeno we can set all of those. Who is peer-to-peer, who is brokered communication, all of those. So we have this Moonbase. You can imagine this in the previous videos as us, the students, using the robots on the side of the send field. So that would be the Moonbase. Then this communicates to the routers down here. So those were Zeno routers in the previous video you've seen. And those will then talk to the different robot modules through Wi-Fi. Those are the dotted lines you can see here. And if we look at what's inside the module, so inside of this arm once again has a router and different components. And inside the arm, we want everything to talk peer-to-peer again, to have maximum performance where we can. However, for the Wi-Fi communication and from the router to the Moonbase, for example, this is not peer-to-peer, this is brokered to have a very high reliability link there, because radio communication is not very reliable. Then we have across the wheels, another arm, another wheel, and all of those have components that are peer-to-peer, but when they want to communicate with the outer world, then they switch to brokered communication that is more reliable. You can also see those links between the arm and the wheel and all of the components of the robot. It's not implemented yet, but we want to have, for example, a wired communication between all of the modules that are connected together. So this is what we want to do. And I have actually also kind of did it using a secondary mesh Wi-Fi network that just connects the robots together. So this actually already worked more or less. I mean, no, it worked on the robot, but using Wi-Fi, not wired communication, this mesh type of connections. Then we have other robots assembly that also are brokered to the central router we have here. And yes, so if you notice this, the robots cannot communicate directly. If you have this robot assembly cannot talk to this other robot assembly, it has to go through the router. So that's what means to be brokered. And the router will manage much better the packet lost, etc., etc. And finally, we would have antenna dish with some orbital station something to then talk to the Earth or other moon bases. This wasn't shown in the previous videos because we don't. I'm sad. We do not have an orbital station yet. Maybe one day. But we actually tested this by controlling the robot through internet several times, mainly because there was some, me or Shami were needed to control the robot and there was a problem. So we just connect to the robot remotely and start doing the manipulation remotely. And actually at the Osaka Universal Exposition of 2025 this year, we were doing some demonstration and movement with the robots. And one day we did 1 or 2 demonstrations that were teleoperated from not inside of the venue, from outside of the venue, from the hotel actually. So even with pretty bad communication, where we go through the hotel Wi-Fi, etc., the network still held up, which is pretty nice. Yeah, so that's for the structure, and yes, for that we use Zeno through ROS, but I want to switch to pure Zeno because I observed much better performances and reliability by only using Zeno. And for the software architecture, you may be asking, okay, how can one software work with that many different robots at the same time with that many different shapes? Especially when we have only maybe me and Shami as the main developers. That's not a huge company working on that. Basically, my way of thinking about it is always let the user do the work. Don't work for the user. So I noticed when I started developing that the user always asks for something that I could not predict when I was developing the thing. And my software never worked for the scenario that we had. And I also noticed that the user knows much better than me what he needs. So I should let the user do most of the code and most of the work, and just provide the user with like an environment in which he can do the work and has as much power as needed. And this also comes from the fact that in our lab, we, especially in the past, we very often began using a new robot. You've seen we actually have 3 versions of the robot. All those versions was developed in like a year or 2. And so it was very hard to adapt the software to those new versions. But by doing this way of letting the user do the work, even if the user is myself, I can very easily switch to a new type of robot, version 1, 2, 3, or begin using a wheel even, etc. And how do I do that? Is I have this structure you can see on the right, where I have the core. The core is not meant to be used by the user. The interface may be used by the user. It depends on what he needs. And I give the user a safe working place, basically. And this is inside of this injection and override blocks. And the user can directly write the code in there. And this way, if he needs a new robot that communicates over, I don't know, an obscure CAN bus, he can directly write the code, I mean in Python, to communicate with this CAN bus. Or if he needs a special ROS2 module, he can then communicate directly with this ROS2 module. It's not my job. It's the job of the user to implement the kind of weird things that he needs for his robot. And actually, the difference between injection and overrides is that the injections are like reusable modules. So for example, you want to apply a gain on one of the motors because you did not consider the gain in your RDF or something like that. I just let the user directly write the gain in the code. This way it's much easier. And there is a small module you can import that you can directly inject to apply a gain and things like this. And this way, for example, if the user wants a gain that changes over time, it doesn't make sense. But it's possible because he has direct access to the code very easily. And he doesn't need to add a whole new complicated stuff to interface. Just change the code directly, and that's your job now. That's how I do it. And then, of course, we have the API on the other side. And the API is not for the robot. It's for the users or the other agents, so the AI, for example, that will control the robot. And this one is much more restricted to be safe to use on the robot. So the injection and overrides block are actually for robot developers, and the API is for the robot user. And that's how I separate everything and can maintain that many different robots at the same time. And depending on where you use the software, the orchestrator will choose which injections or override to load onto the robot. And so that's how we can adapt that quickly. And here's some more videos, because I don't want to speak too much about theory. Here, for example, I don't know how many robots, but this is version 1, 2, 3, and the 4DOF arm, and I control all of them at the same time. This is not just mirrored joints, it's really different robots loaded inside of the software that are all being controlled at the same time.
This is Gazebo, right?
No, it's not Gazebo, it's just RVs directly.
Okay.
So no simulation. If I can play the video. Okay, switch to the next slide. Can I get... Okay. I just wanted to show something else, but apparently Google doesn't want to let me. Oh, yeah. I think around the end, yeah, here I just use the user interface that Shami did, and I'm going to select more of those robots down here to make them move. And they also started moving with all of the other robots. So like you can see it works in runtime to consider more or less robots that are all different with different DOF, etc. It's actually pretty cool. And those were all robots in parallel. We can also put them in series. So here I'm doing end effector control of moving back, up, down. And there are, I don't know how many DOF there are on this, but it's 4 robots, one after the other. And they are moving using inverse kinematics, forward, up, down, doing all of the computations of the joint angles to do that. So that's also pretty cool. We never did this in reality because we don't have a robot capable of doing that, but it is just fun. And finally, this is more on the API side. You might be asking, okay, how do you make the trajectory for all of those different robots? Isn't it very hard to know, okay, this motor is slow, this motor is hard, not hard, this motor is slow, this motor is fast. How do I keep them all in sync so the trajectory doesn't become a gigantic mess in the end with that many different robots? Especially when we want to launch a new type of robot. I actually don't want to fiddle with 10,000 settings to say, okay, this motor speed is that, this motor speed is that, etc., etc. If I could, I would like to not do any setting. And actually, that's possible with this software because all of the trajectory and adaptability actually happens at runtime. So here you can see I'm currently synchronizing the trajectory of actually 6 different end effectors. So there is the big MoonBot here. There is a small real-man robot, it's called, here in red here. And then there are 4 end effectors for this small quadruped in green. And here, if I use my hand and just slow down one of the limb, you can see that the trajectories of all of the other limbs also slow down and wait for this limb to continue moving. So they all wait for each other before continuing the trajectory. And to handle also network problems, you can disconnect the limb, and if the limb disconnects, or if any motors disconnects, it actually stops the trajectory. When the limb comes back, it continues the trajectory. So this was initially developed because of network issues, but it also works if you just unplug the leg directly on this robot, which is also pretty cool. And you can, of course, disconnect more than one leg. You can do pretty much anything. And as long as the trajectory is able to continue, it will just continue. And if I also unplug the power of this small robot, you can see the robot falls. And then the motion stack software will then make it stand up again to go back onto the trajectory. And then the trajectory will actually continue. So that's also very cool and very safe because we want safety first, also because if you want to go on the moon, we cannot break the robot. We cannot repair it, so it should not fail. And also I want safety because we work with students that do not have a lot of experience working with robots. So it can be very dangerous. And as you know, those robots are like 20 kilograms. So it's very dangerous to work with. So I don't want anything weird happening on the safety side. And yeah, actually all of those videos were taken from one single experiment that lasted 12 minutes, where the controller just continued doing the trajectory without me doing anything on the software side. All I did was unplug stuff and try to break it, but it continues. And that's the end for me. If you want the motion stack software, it's here. And yeah, we are looking in the future into using Zeno instead of ROS for improved reliability and making, I think, robots open source, because this is just the core software. All of the robots with the URDF, the launching system, is not open source yet because of patents and things like that. But the core software, if you want to use your robot, it's here.
So how are the wheel modules? Are they also controlled by this?
Yeah.
Or
Yeah, they are also controlled by this, actually.
okay.
We just don't start the inverse kinematics on them, and we can just control them normally.
Yeah, and also because of the synchronization that Elian was showing, it's not only on end effector synchronization, but also it's
On the wheels.
on the joint level. Yeah, for example, you can show the cargo, I think.
I think the Shinkansen stuff.
Okay, yeah.
If
For
I have it.
example, this one, yeah. So that one is in your paper video.
Yeah. Oh, yeah,
Yep.
this one.
So, for example, in this bullet train Shinkansen video, we have 4 different wheel modules. Of course, we have the arms as well, but at the moment, as you can see, also the versions of the wheels are different. Actually, the size of the wheels is also different. So, of course, there's like some gain and stuff we tune on the lower level side, so they kind of move at the same speed. But the motion stack handles the synchronization of the wheels as the joint on joint level. So all of the wheels which are controlled, for example, in this case, it's 1, 2, 3, 4, 5, 6, 7, 8. 8 joints are controlled at the same time, and if even one of them loses some connection or breaks or it just dies, explodes, anything. So if it's not continuing the trajectory, the control trajectory, then other ones will wait. It will just stop, and that's
So if
also really good.
Basically, if one wheel stops, all of the wheels stops to stop the train and not break the train.
Yeah.
So imagine if the front wheel were to lose connection and stop moving, then the other wheels on the back should also stop to avoid breaking the robot. So that's one advantage of the synchronization that works on end effector and on inverse kinematics also.
Yeah. On the end effector, actually, can you show the tricycle?
On end effector and on motors, sorry.
Yeah. Can you show the tricycle going up and down again? There, actually, you can see clearly that one of the motors is slow, actually, because it was a bit...
this one.
15, yeah. So here, for example, it's going down and going up. It's using 3 different end effectors to control the body, right? And in this case, one of the legs, actually one of the motors in one of the legs, is a bit slow. It's mechanically a bit malfunctioning. And in this case, what happens? The other arms will wait for this motor to reach first. So they will not deviate from the trajectory like that much, because the one that is slower is not, they will wait for him to catch up, basically.
Yeah.
So in this case, it's really good in that sense that they are all connected to a single body, and if one deviates a bit more, this body will tilt. If it's a really noticeable amount of deviation, then it will just break, because there will be too much torque and stuff like that. And this is in this case especially, like, you can see how useful it is to control different robots and synchronize them. So you can control stuff like this.
Because we don't want to have one leg pushing up while the other legs are stuck. That's when you are connected to the central body. They should all be at the same height.
Yeah.
Do the wheel modules and the arm have the same like controller board, or are they like heterogeneous?
They have the same.
You mean lower level or?
Yeah, the lower level like hardware used
yeah.
to the CPU
Like the hardware,
and
yeah,
like
it's the same.
yeah.
Actually,
Same.
the low level we also developed. It's not anything like open source or something. Like, we just developed it from scratch using the normal, the command libraries and stuff like that, of course. And those things we developed in a way that is also modular. So we have only one low level controller, and it works for all the robots, like whether it's an arm or the wheel. It just launches the correct correct way, and it's heavily inspired on the launch API of the motion stack. So it's kind of working in the same way and knows what to launch. The robot itself knows what motors it has, what it should launch, and stuff like that. Yeah.
And we have this Maxon motor on this robot.
Yeah.
But we actually use O-Drive on another robot. The 4 degrees of freedom one uses O-Drive. And on the very small quadruped, this one is another type of motor. Those are dynamic cells.
Dynamics. Yeah.
And the other one, the one in this video. So dynamic cell on the black one. No, dynamic cells on the green one. Maxons on the blue one, and the red one is Realman. I don't know which kind of motors it uses, but it's a different controller again.
Yeah, actually, this quadruped is it's called MoonBot as well. It's called MoonBot Zero. Yeah, so this is the first
iteration,
first concept basically of the modular robots. That's why the legs are also, they can be detached and attached back, and they work.
Why
you can find
legs?
The open source paper about this. MoonBot Zero is fully open source.
Cool. And for MoonBot Zero, why did you choose legs and not wheels?
Because it was earlier in the project. That's it. We didn't.
Yeah.
But it was already for a moon environment with Regolith, right?
Yes, exactly.
Okay.
But I don't know who made the decision. It was made before you arrived, so I really don't know.
Yeah.
And so there was a revolution. You made a revolution, and everything moved to wheels.
Yeah, exactly.
Yeah.
So I started developing the software, and I was there doing quadrupeds, and all of a sudden we had 7 DOF 20 kilogram robots with 20 kilogram wheels in the lab, and now I have to switch everything to this.
Yeah.
So that's why it became so modular and that deeply modularized, because the robot kept changing a lot, and we had to adapt fast.
Right. Yeah. At the beginning, you focused directly on the robots, and you skipped, the describing the goals of the project. Okay. And I don't think we were. For me, what was interesting, because I know a little bit. I think one of the goals is to build, right? To have robots to build buildings, right?
Yeah.
And
Exactly.
can you tell us a bit more like that, how the robots are more adapted, and perhaps one of the reasons to move to wheels?
First, wheels are better to transport loads. Obviously, they use much less power, so that's why we want to use wheels more. And actually, our team focuses more on not building structures, but building robots. So that's why we were more focused on that. But here there is more of a video of a building task. And the goal is more to build stuff. So we had deployable solar panel also video that we've seen. This is part of this goal to showcase that we can build and assemble stuff. As to what do we build, I genuinely don't know yet. Because you are a bit more focused on the.
But it could be to assemble a solar array, for example, right?
Yeah, exactly. Yeah. Solar array, or if you see actually this white thing, that's actually hard to grasp what it is. I'm sorry, I don't have a very good video about that. Maybe I have something that's
on the demo video, maybe.
Yeah, that's an inflatable module. Yeah, it pops up, and I don't know if you can see. Can we see it? Yes, in the back here where there is my mouse cursor. Yeah, it's pretty big, and here it's deflated, and the goal is to then build this structure. But the easiest way to build something is just to inflate it, and so it gets inflated, and then it forms some kind of habitat or something.
Yeah.
So there are
Actually-
some projects. Oh, please, Fami, sorry.
Oh yeah. Regarding just about this is actually like basically a research project that is also in the same like category of the project, kinda. So this is from
project.
different university, Moonshot, and this is from university in Tokyo, and I think it's Institute of Science, something like that. So they work on this, and what they do basically, this habitat they're working on, it inflates, and actually it has different cells, as you can see there, and by deflating and inflating these cells, it actually can roll. So this one is a concept of like inflatable living module, or for example, research module, whatever. Like inside it will be constructed later, but basically that's the skeleton that just inflates and becomes like somewhere where people can go and live. And the interesting part is that this actually, you said it's big, but this is just a half size. The diameter of this one is 2 meters, and the real size, the original one, is 4 meters. So it's even bigger. Yeah. So that one is also a really interesting project. We don't work on that, like we collaborate, of course, but we don't work on the development of that. That inflatable module.
Venkat is asking, where would you inject machine learning in this architecture and what type?
Do you have videos?
We already have
some. We can
I
show.
don't know if you can find them. Then switch to presenting your screen.
Yeah,
I don't want to show something that's forbidden publicly, so I'm gonna keep on my slide.
Let me think.
Yeah. But yeah, this the movement actually of the robot in this video, when it goes towards the inflatable module, is actually machine learning. It does look smooth, so you don't see the difference, but it's actually a totally different algorithm, and I think it was joint control. I'm pretty sure. It was machine learning for detecting the target also.
Okay, so this is something that I know I can show. This is work of another PhD student from our lab. Let me okay, this one. So this is a paper that is like the preprint is already available publicly, so I know I can show this. Yes, the idea of his work is that, as you know, of course, because we have different modules, it's difficult to have the policy get trained for the whole configuration. So what he decided to do is work on decentralized RL and basically train the policies for separate modules. For example, you have the wheel module policy agent, you have the arm, and etc. And using some state machine at this point, it's they will know where they are, and that's one of the inputs of the policy in this case. So using this decentralized policy stuff, for example, in this case, it detects the wheel, and using the decentralized RL, it will approach it and then switch to another agent that is working for the manipulation. And it will grasp the wheel using the manipulation policy, and then it's teleoperated to detach the gripper and stuff like that. Of course, the ideal goal is to have everything fully autonomous, running by different policies and stuff like that. But this is, of course, work in project. Also, and for example, this is one of the ways to have the RL working. Of course, you can say this is something that can be done by classical control, but I think, of course, there's many things that can be done in a classical way, but it's always interesting to research the other ways of doing this and maybe comparing which way is better, easier, cost effective, and stuff like that.
especially this is interesting to have AL work on a wide set of robots, because usually one AL policy is focused on one robot only, where here we want to work with a wide, with diverse robots without needing to retrain every time we change the shape of the robot.
Yeah.
How do you deal with the notion of identity? Because you have module identity, but you also have assembly, so robot identity. And so when a module is part of one robot, and maybe after at some point it's part of another robot, how do you deal with identity then?
Yes, actually the identity is not handled at runtime. This is handled at launch time. So if we change the shape of the robot, we have to SSH on the robot and change the few configuration, actually just the name of the robot in the assembly, and relaunch this. And we found that like assembly handling at runtime is really not very useful. It's because you SSH on it, it takes what, 30 seconds maybe to update to close the software, update the file, and relaunch it. So it's better done manually, especially as it's much safer this way. You will not launch the wrong thing, etc. And it's not a huge loss of time.
Yeah.
And for identity, we just set an environment variable on the on the robot, and the launch system will pick it up and understand, okay, I am robot number one. So because I am robot number one, I should launch this part of the software given this assembly. So basically it extracts the assembly. Look, okay, am I inside of the assembly or not? If it's not inside the assembly, it does nothing. If it's inside of the assembly, it only launches the modules associated with it. And we also do that for simulation, actually. If you run the software on your PC that is not a robot, then your environment variable is not set, it's none. And if the environment variable is none, then we launch the entire software in simulation mode. This way, students can just run the exact same things as the robot, have the exact same environment, and just when they launch it on their PC, they have the simulation directly.
Okay. Yeah. So the notion of identity becomes more like a mechanism of inheritance, right? It's a module
Yeah, exactly.
identifies in which assembly it is, and the identity comes from that. Right?
Yeah.
Okay.
And then we have the MoonBot hero, which is the heavy one with 7 DOF, kind of identity that says, okay, you have 7 DOFs, you will load this URDF. The MoonBot will identity that, okay, you have a will, so you do not launch the inverse kinematics. And then it inherits from that. You are will version 1, 2, 3, which other parts you should launch. If it's the MoonBot G, this one is the small one with 4 DOF. It also loads from the limb categories, but only changes the number of DOF and the URDF, things like that.
Yeah.
Well, thank you.
And also it's the same way, kind of similar way for the low level, as I mentioned before. It will change on the launch time. It will change how it's supposed to launch the low level as well. Like for example, how many motors. It's so one file will handle. Okay, if it's an ARM, it will launch 9 motors communication. If with the drivers. If it's wheel, okay, which one is it? Some of them has 4, some of them has 3, some of them has 2 motors. So all this is handled on the launch time, and yeah, everything is just handled by the launch API.
Yeah, and it's also easier to debug if it's only launch time and not runtime.
The debug must be a lot of fun.
Oh yeah.
Yeah, that's.
Do we have other questions, perhaps in the chat? No, we're covered.
One reason to hot swap identities is combination failure to low latency and safe crash mode. Hot swap identities is combination. Okay.
Yeah, I think we answered most of those. It was your question, Eric. Okay, that's why we answered it.
No, I think what Venkat is alluding to is that in general, maybe the robot has a mission, okay, but there are a lot of errors and failure modes and so on, right?
Yeah.
Okay. And so if the identity cannot hop swap, with for example 2 wheels coming to replace 2 broken wheels and the reconfiguration.
Yeah, I was thinking of that type of thing. I was in particular thinking of research my ex-postdoc advisor did at ETH with drones. So with drones, since the dynamics are so much faster, if one rotor fails in midair or something, you have to reconfigure the whole stability to run on 3 motors. You don't have time to SSH in and redo a launcher type protocol, right? You kind of have to like immediately adapt and notice that you've like broken down and operate differently. So but it's a special set of circumstances. I think you're right that in most slow rover type situations, you can just stop what you're doing, SSH in, and reboot.
Yeah. And it also reboots fast, like 30 seconds it's done. So that's nice also. If it took 10 minutes, I think we would not do that. Yes, it looks like Swarm a little bit, indeed.
Yeah, we are 20 minutes past, but thank you for it was really interesting. So your project caught my eye because, like, I don't know how much Eric has told you what we are doing. So, so this is our robot. So it's like a wheel robot, and then we were planning to add some manipulator. And a lot of the ideas you guys have. So we have been discussing also that, but from a toy robot perspective. And then when I saw your project. So I found it really interesting that we have been approaching it from a very use and throw kind of robot, but kind of converging on the same ideas, right?
Yeah, exactly.
Yeah.
And on your robot, what's the computer on board, etc.?
So we are doing everything open source. So right now it's an ESP32 Wi-Fi. So this is basically a $70 Amazon robot you can buy. And then it comes with a AVR small microcontroller, and it didn't have Wi-Fi. So what we did was we want to one of the threads we are also researching is controlling the robots via crypto and blockchains, right? So that you could have some identities and a lot of crypto affordances for the robot, and for that you need to connect the robot to the internet. So what we did was we designed a custom PCB that has basically ESP32 Wi-Fi. So right now it's designed in the form of a RPi hat. So basically the idea is that you would connect the RPi like this, and then have the controller board on top of it.
Okay.
Yeah. So and then Venkat also had some idea of connecting a manipulator arm on top of this, and then we were also thinking of how these. So I have one more of this robot, and then how they could connect with each other. So a lot of the ideas you have it. Yeah, but our idea was on the moon, when the launching costs have come down, you could send this is 1 kilo or something. So you could have fun robots, which you could just throw away. Yeah. So you could have two, three of them together, work together, have some fun, for normal people. Yeah. So that was the research sites we have been doing here.
Yeah, that was very nice.
And there is also all the discussion that is related to identity and so on with the cryptobiotics concept from YaRG as well. So it's a mixture with crypto technology, okay, but for very concrete reasons.
Yeah, but I would like to use your stack, Alien, the open source stuff you have made on our robot, and if let's see like what I can do with that, because like I have 2 of the robots with them. Maybe I'll buy a toy manipulator arm and then try to do something.
Yeah, you can try. You can try.
Yeah. But thank you. Like your presentation was really good. Are you guys going to iSpar? I was thinking of going there, but maybe it's too late now. Yeah.
Yeah, we will be at Typhoon.
Yeah, we will present, but it's still, I mean, I think it's still open. It's not early bird anymore, but yeah.
And our robots will be there during summer.
Oh yeah, we'll bring the MoonBots to present. Actually, the last version.
Yeah.
Cool.
Does anyone have more questions, comments?
Just thank you. It was very
Yeah,
interesting.
thank you. That was amazing.
Thank you so much.
Thank you for listening.
That was great. Yes.
Thank you very much.
Thank you. So, good day, good week.
Okay then.
Yeah.
Bye.
Good week, everyone. Bye bye.
Bye.
Thank you.